All right. So in these last two lectures, what we're going to do is we're going to finish up our discussion of forces, and we're going to be treating the first really new topic to many of you taking AP Physics, which is air resistance. So we're actually going to be talking about objects falling in the presence of air, and there's a special type of friction that occurs when things fall in the air that requires us to really bring in calculus to understand the equations of motion and what's going on. And that's going to be a really good way for us to wrap up forces and then get into kinematics. So I don't plan on putting this whole topic on your exam as far as solving the calculus equations go, but you will need to know how to set them up. So with that in mind, let's get started. So to kind of jump in Physics 1-2 we dealt with objects falling in the absence of air resistance, so things just had plain old gravity. The acceleration was always 9.8 meters per second squared. But now we're able to actually take air resistance into account because we're going to be using calculus in this class to really derive the equations of motions of systems in the presence of air resistance. And that, in fact, is the goal of any problem in physics. You have a system, you draw the forces on it, and from those forces, using Newton's second law, you write down the sum of the forces equals mass times acceleration. And from that acceleration, you try to derive the equation of motion, by which you mean the position, the velocity, and the acceleration as a function of time. That's what we mean by these equations of motion. So in this class, we're going to deal with two types of air resistance. We're going to deal with linear air resistance, and that means that the air resistance depends on the speed that the object is falling, times, this constant k that I put in front, and that k basically just means, its shape and what it's made of and all that kind of stuff, and we just lump it in this. It's an engineering constant you measure. What we're basically saying is the air resistance depends on the speed times some kind of constant, and also we're going to deal with quadratic air resistance, which is negative bv squared. So either air resistance depends on the speed, or the speed squared times just whatever factor we put in front, which is like it depends on, again, the shape of the object and what it's made of and all that kind of stuff. So what happens when real objects fall? Well, first, at the very instant that they are released, there is no air resistance at all because there is no force. That means their acceleration to start with is just g, 10 meters per second squared. And the net force on the object at the very beginning is the weight on the mass due to the Earth. However, as we fall faster and faster and faster, the air resistance is proportional to our speed, or our speed squared, which means the net force on the object is decreasing because you have weight, which was the original net force, but now there's air resistance opposing that weight force, so the net force decreases, as does the acceleration. Eventually, what's going to happen is you fall fast enough that your air resistance exactly balances the weight. So you go faster and faster and faster, and your air resistance gets bigger and bigger and bigger until finally you reach a speed that is so high that your air resistance force exactly equals the weight of the object. What happens then is that the object is at a speed called its terminal speed. It travels at that speed until it hits the ground, because now there's no net force on it, but it's already moving. So according to Newton's first law at that point, the net force is zero. So if there's no net force on the object, it travels at this terminal speed, which we call vt, and it travels at this constant velocity until it actually runs into the ground. So there's something really important here in this last slide that we need to be aware of. The thing moves faster and faster and faster until it reaches terminal speed, and yet its acceleration decreases. Now, as somebody who's very experienced in physics, that statement is absolutely fine, and it makes perfect sense. It'll also make sense to somebody who teaches calculus or knows their calculus really well. But the very first time a physics student sees this sentence, it's something to wrap your head around. So I actually want to just pause. I want you to sit with those words and sit with your discomfort. It's kind of good to pause the video at this point and write that point down. So something moves faster and faster as it falls in the presence of air resistance, and yet its acceleration gets less and less. So let's talk about how that can happen. Well, here's just sort of a table of numbers. These are hypothetical numbers, but this is an example of something falling faster and faster. Its speed increases, but acceleration decreases. So when something first falls, it's got an acceleration, say, of 10 meters per second squared, and its velocity would be 10 meters per second, say in 1 second. I'm just making up some numbers. These are not. This is an example mathematically of how can something move faster and faster at its acceleration decrease, and I'm showing you that example right now. So say after 2 seconds, say there's air resistance and acceleration goes down to 8 meters per second squared, and its velocity would go to 18 meters per second. So in the second, it doesn't gain. It doesn't gain as much speed. It still gains speed. It gains 8 meters. It's traveling 8 meters per second faster because its acceleration is still positive, but it's less. And then, say after 3 seconds, let's say its acceleration drops to 6 meters per second squared, and its velocity would only go up to 24 meters per second. So if you notice, in the first second, it gained a whole 10 meters per second speed. In the second, it was only 18 meters per second. If we're going at the same acceleration, its velocity would be 20 meters per second, but it's not. It's 18. And in the third second, it gains even less speed. And of course, what happens then is in the fourth second, it gets even less. And then in the fifth second, less still. And then in the sixth second, let's say its acceleration goes to 0, notice its velocity stabilizes. So it's actually falling now at its terminal speed of 30 meters per second. So in the first 4 seconds, it gains more speed. But if you look at the rate of its gaining speed, which is what acceleration is, it gains less speed with each instant until finally its speed levels off. So this is a really good table to kind of sit with to understand the idea of how something can move faster and faster with a decreasing acceleration. And then in the 7th second, again, terminal speed. Its acceleration is 0, so it gains no speed. It just coasts at that speed of 30 meters per second until it hits the ground. So what would acceleration look like graphically in this case? So you have your acceleration measured in meters per second squared, and your time is measured in seconds. And I've marked 10 meters per second squared as that letter G. So we start off with that acceleration at time equals 0, and what happens is the acceleration drops off in the first second. In the second, it levels off a little bit more. And what happens is that it slowly approaches an acceleration of 0 meters per second. So if you were to ask to graph the acceleration of an object falling in air resistance, the graph looks like this. And again, you start off with a really high acceleration, and that levels off to 0 meters per second squared as time approaches infinity. So that's an asymptote. Okay. So the acceleration goes to 0. Okay. So now we ask the question, what would velocity look like graphically? So we get our axes labeled, and notice I've labeled some speed, which is going to be the terminal velocity, which means that we get speed. And as we gain speed, there's more air resistance force, and then finally air resistance balances gravity, the net force is 0, and according to Newton's first law, we continue in a straight line at a constant speed at the terminal velocity. So we start off with a speed of 0, and then we have, in the beginning, quite a bit of acceleration, so there's a steep slope. Then the slope actually gets a little bit less as v versus t gets less, but still we gain velocity because we are still accelerating, and it levels off until we approach this terminal velocity, and then we level off at the terminal velocity. So this is in fact what the velocity versus time graph looks like when you have air resistance, regardless of the kind. Finally, let's take a look at what the position looks like. And again, we label our axes, and our position graph kind of looks like the velocity graph, but let's be careful. Notice, again, we do start off with an acceleration that levels off, so we cover a lot of distance in the first amount of time, and then a little bit less in the second and third. And then notice that I've left a little space here. I want to be clear, at some point we reach the terminal velocity, and what happens there is that our progress becomes linear with x versus time because we are coasting at a constant terminal velocity. So in this region here, we have a linear region with a slope that is exactly equal to that constant terminal velocity. So what I want to kind of get into now is one example problem. So suppose, again, we've got two types of air resistance that we deal with, linear and quadratic. Those are the ones that we actually solve and deal with in AP Physics. And remember, air resistance always opposes the direction of your motion, so be very careful when you label that. And when an object falls, of course, there would be two forces acting on it, air resistance and weight. So when we look at a specific problem, say we've got something falling and there's some air resistance and weight, and at the very top of its trajectory, right when I release it, notice that there's no air resistance at all. It hasn't gained any speed, so there can't be any air resistance. As it falls, it gets a little bit more speed, and the air resistance gets bigger. Finally, we reach a point where the air resistance exactly balances the weight. So we've been speeding up to now with a decreasing acceleration, but now we finally reach a point where the air resistance exactly balances the weight. The net force is 0, and the object continues in a straight line at a constant speed at the terminal velocity. So now, let's say that we have linear air resistance, kV, and we'll get that negative sign back in a second. So what that means is the weight and the air have a tug of war, and the effect is that the mass accelerates. So this is nothing new. You've done this in free body diagrams before. And of course, for weight, we put in mg, and for air resistance, we put in kV. Now, here is a little bit of something that we want to do that we haven't done yet, which is suppose I say, hey, get me an actual value for the terminal speed in terms of these variables on the left-hand side. Well, what happens when we have terminal velocity? Let's start with the equation. We have mg minus kv equals ma, so that's from Newton's second law. But at terminal velocity, we stop accelerating because there's no net force. If there's no net force, the acceleration is 0. That's what Newton's first law says. So what that means is, at terminal velocity, the weight exactly equals the air resistance force. And so we can solve for the terminal velocity by rearranging like that. This is actually a calculation they have you do on the AP. So if you actually want to know what the terminal velocity of an object is, you take the weight and divide it by this constant k. Now, another thing they'll ask on the AP when you have this air resistance type problem is, write but do not solve a differential equation. And you can kind of read what it says there. So here's what we're going to do. We're going to write mg minus kv equals m times. Now notice I've done a little bit of calculus here that you learned in a different class. The acceleration you learned from calculus class is the derivative of velocity with respect to time. We're going to talk about that more in class a little bit, but in this lecture, what you do is you rip out the a, you put in dv dt. And then you can actually isolate the dv dt. And that's what they mean by getting the differential equation. Now, what we're going to do next is we're going to solve that equation. So our goal in physics is to write down Newton's laws for a system and determine the position, velocity, and acceleration of a system as a function of time. That's actually what physics is. Take forces, write them down, and then from those forces, tell me where a particle will be, what its speed will be, what its acceleration will be for all times. So this equation is the one we want to solve from the last slide. So this is the equation that we have, and I'm going to do quite a bit of algebra here. So the first thing in calculus, you know, is that you can treat dv dt as though it were a fraction. So I'm going to multiply both sides by dt like this. And then, for those of you that know some calculus, I'm going to divide by g minus kv over m to get the v and the dv stuff on one side and isolate the dt. Now, I'm going to use a technique that you will learn in second semester calculus if you're in AB, and you should have from last year if you're in BC. We're going to solve by substitution. So I'm going to get u equal this huge thing in that denominator on the right side. I differentiate, and then what I'm going to do is I'm going to rearrange to isolate dv. Good. Now I substitute that back after taking the integral of each side, and then this is the integral that I get. Let's do a little bit more rearrangement of terms. Let's get isolated du over u on the right-hand side. And now what I'm going to do is I'm going to integrate both sides. Now here's the thing about integrating both sides. In calculus, the integral of du over u would be natural log of u plus c. In physics, I'm going to write this c in a very strange way that helps me solve the problem. So watch this step carefully. It's annoying and tricky. So I get the left-hand side you could predict. The right-hand side, it looks like your calculus book, but notice this is minus the natural log of c. That's what I'm going to call the constant in AP Physics. Now I'm going to do some algebra. I have this thing, so I'm using a rule from algebra right there. I exponentiate both sides. And now I rearrange like that. Now what I want to do then, after substituting back for u, which is what I do here, is I note that at t equals 0, v equals 0, and I plug in 0 for t and 0 for v. Again, when time is 0, I'm not moving. I plug that in, and what this does is it allows me to solve for the capital letter C. Substitute that back in, rearrange, and finally, here's my solution. You might have to stop and watch this a couple times. I would freeze this frame and write this proof down. And we'll actually catch up next time in class and talk about it a little bit more.